So what are we on? Lecture 11? Sound about right? All right, so this is lecture 11 of operations research. What I want to do today is I want to talk a little bit about phase 1 of the simplex method. And then I'm not going to do phase 2 today. I want to talk about some of the homework problems. I found one of them particularly interesting. Any idea which one I found interesting? Yeah, the Queens. I think the Queens is really interesting. Whoever came up with that, I really want to talk to them because that killed a huge part of my evening last night. But there's some really good ways of attacking this problem. So far, the best I've heard from a class member is 11. Has anybody been able to do bigger than an 11 by 11 board? All right, so there will be some prize for getting the largest board possible for this problem. There's a lot of really good mathematics behind this, and both on the theoretical and the computational side, I think it's worth discussing. All right. In some sense, Tuesday, Thursday classes are better because you have a longer period of time. You don't have all this stop, 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 stop where you keep reviewing the material you've already done. But it's also not a bad idea to have this stop, stop, and review what you've done. So saving a little bit of time by just writing things ahead, we have the simplex method. Here's the canonical form of the linear programming problem. I've got ax equals b, x greater than or equal to 0, and I want to minimize c transpose x. We show that essentially without loss of generality, we can assume the following four conditions. If a is not m by n with m less than n, then the system is going to be overdetermined. And then it's not going to really be that interesting or that applicable to the real world problems we want. In all the applications, m will be significantly less than n. The next one is the rows of A being linearly independent. If the rows are not linearly independent, they either repeat each other or they give you an inconsistent matrix. So this is, again, not a big deal. I don't know if we ever explicitly say a column is not identically 0, but if a column is identically 0, the corresponding variable is never involved in the action, and you could just remove it. B is not a linear combination of fewer than m rows. This one is actually non-trivial. You cannot always assume this, but if you think about it probabilistically, if you choose a vector B at random, for it to be a combination of fewer than m rows, it's got to lie in a lower dimensional space. Now you have an m-dimensional space. This would be lying in unions of these hyperplanes. And the hypervolume of that would be 0, so without loss of generality, we'd like to assume this. If we can just tweak the elements of B by just a little bit, that's not going to be a problem. And then the last one is B is greater than or equal to 0. Turns out that's actually not a big deal at all. All we have to do is, since we have equality here, if an entry of B was negative, we just multiply the corresponding row of A by -1. So the whole point of this is it cleans up the formulation. We've already seen in previous problems how nice it was that we could assume we had a canonical linear programming problem. It cuts down on the number of cases we have to break things into. For those of you who are trying the chess problem, you could use symmetry to speed up the code at the cost of more complicated programming. And so that's hopefully a really good reminder of the advantages of simplifying the description of the argument. All right, so here is the simplex method in high-level bird's-eye view. Phase 1, find a basic solution or prove none exists. Phase 2, given a basic feasible solution as input, find a basic optimal solution, or prove that there is no such solution, that there's no optimal solution, by explicitly constructing a sequence of feasible solutions with cost going to -infinity. Now, this is extremely bird's eye view. I haven't actually told you how to do either phase 1 or phase 2. So let's get a little bit better. So here's the idea of proof. So assume can do phase 2. Show can do phase 1. Now, use phase 1 to do phase 2. Okay? So we briefly mentioned on Friday's class why this seems ridiculous. What's wrong with this outline of proof? Yes. So I think I said you should replace the QED symbol with this new chicken and egg symbol. But this is absurd. So in order for this to work, we've got to be very careful. We cannot assume something, use it to prove something, and then use what we've just proved to prove what we assumed. Because here, when we're doing this argument of phase 2, we're using the result of phase 1, which we only got by assuming phase 2 works. So this is the most interesting part of the method, and it's really worth hammering home. It's not because I don't have enough material for today's lecture, okay? It's because this is the key idea. What was the word to describe the chess problem we were doing in class? We didn't look at the original chess problem of putting down 5 queens. We looked at what kind of problem? Yes?
Duality.
We looked at duality. We looked at a similar problem. We looked at a related problem. We're going to do something very similar here. What we're going to do is we're going to use the method of phase 2, not to the original problem, but to a related problem, where we know a feasible solution exists. And then we can run through. So again, one of my favorite methods of proof is the method of divine inspiration, where you write down the answer. And then you just check and see that the answer is right. It's a wonderful way to prove things. It's unfortunately not always reliable. You cannot always count on being divinely inspired. But when you're divinely inspired, life is good. You write down the solution, check and see it works. In a large class of problems, we know a basic feasible solution exists. And I am definitely glad that this is being recorded right now. I am quite furious with American Airlines. They have screwed up my travel for December. Right now it looks like I may not even be traveling with my son, who may be put on his own flights. So, I don't think American Airlines really understands a lot of things. But can someone give me a valid schedule for American Airlines that will satisfy all constraints? No. Really simple schedule for American Airlines.
Don't fly any planes.
Don't fly any planes, yes. And in fact, I would conjecture American Airlines is really close to that simple solution right now, based on the number of flights they've just canceled on us. It will work. It will satisfy all the constraints. You won't have the same plane being used on 2 different routes at the same time. You won't have pilots having not enough rest time between flights. They're going to have plenty of rest time. All the rest time they need. Okay? That will satisfy all the constraints. How much money will it make American Airlines?
Enough from the government, at least.
Well, not just the government, also for me, they're not refunding our money. So, they found a nice loophole. But in general, if we could actually get our money back, would they be making money if they don't fly planes? No. So they would want to fly planes, and then you would start with a feasible solution that exists, flying nothing, and then you would start working on it. So a lot of times, if we want to use phase 2, we need to put in as an input a basic feasible solution. It may not be hard to input that basic feasible solution. Okay? So for a lot of problems, we know the basic feasible solution, or at least a basic feasible solution. The question is, no matter what problem I give you, can we find a basic feasible solution? So does every linear programming problem have a basic feasible solution? So give me an example of a linear programming problem, since I saw some heads going, no, that has no basic feasible solution. Yes?
So if you have like a diet problem where you need a certain amount of nutrition, but there's also a restriction on like cholesterol or something, that's below the bounds of the
Sure. So maybe you need to eat a certain amount of each food, but if you eat too much of certain substances which are in these foods, you die, and so you can't have enough. A really simpler one is, x equals 2, x equals 3, x greater than or equal to 0, minimize 2x. Here is a really dinky, simple linear programming problem where there is no feasible solution. Okay. So it's nice sometimes to just quickly write down something very simple to just know that there are issues. Not every linear programming problem will have a feasible solution. So I can't always generate a feasible solution. What I want to do is I want to show that if there is a feasible solution, I will be able to find it. And if I have a feasible solution, I'll be able to go from that to a basic feasible. We already know how to do that.
Can you define again what it means to be a basic?
So basic feasible solution means that if you look at the non-zero entries of your solution, the corresponding columns of A are linearly independent. So what we want to do is we want to study a related problem. And so again, this is in a similar spirit to the chess problem, where we made enormous progress by looking at a related problem. We should still have AX equals B. right? We still want that. The problem is, can we always solve AX equals B? What would be the easiest matrix to replace A with to try to solve AX equals B? The identity. So let's expand. So now we have x1, x2, xn, z1, zm. So these will be our new variables. And they'll be greater than or equal to 0. And we're going to expand our matrix. We're going to pad our matrix to A, and we're going to have the identity matrix next to it. And then we'll put the x vector and the z vector here equals B. So this is our new expanded matrix. Yes?
It should be as greater than, right?
No, I want to have more variables. I want the system to be underdetermined.
Yeah, right.
And so I want to have more variables than rows. So think of it as just the special case here. If m equals...
Right, so we should have more columns than rows, right?
Right.
Shouldn't that be m greater than?
M is the number of rows, n is the number of columns. So when we look at this, we can now begin to see why I added a fourth condition. Well, let's get some of my exercise for the day. Come back over here. We said B was greater than or equal to 0. And at first, why would we want to add the constraint B is greater than or equal to 0? Well, remember, when we were looking over here, we assumed x was greater than or equal to 0, and we were always looking for something like that. Now, when we come back over here, and we're trying to solve things, now that B greater than or equal to 0, we're going to be fine with the Z is greater than or equal to 0. So that this is really an expanded version of our original problem. Can anybody give me a solution to these constraints? I want to solve this subject to, I think there's a really simple solution that has to exist. There's a feasible solution staring us in the face.
X is 0, Z is B.
Yeah. Take x equals 0, Z equals B. If we do that, then we'll clearly solve these constraints, and everything will be non-zero. Is this a canonical linear programming problem right now, or is it missing something?
What is the dimension of B in this case?
B would have m components.
Is it also extended or not?
No, B is not extended. Because when you do the linear algebra multiplication, you have m rows and n columns.
Right.
Now we have n plus m columns and n plus m variables. So we'll still get m entries. Is this a canonical linear programming problem, or is it missing something?
Needs a cost.
It needs a cost function. We have the freedom to choose a cost function. I want to choose a cost function that's good. So the cost function, if I want to minimize z1 plus z2 plus zm. So we're looking at a new linear programming problem. And we're doing one where it is easy to find a feasible solution. And in fact, not only is this feasible, is it basic feasible? Yeah, everything that's non-zero is going to be just the entries of z, right? Which correspond to I. And we're assuming B is not a linear combination of few of them. Well, some of the entries of z could be 0, but that's fine. The corresponding entries will still be linearly independent. So this is also feasible. This is basic feasible. So the whole point of phase 2 is we need to be able to input a basic feasible solution, and then we can run the machinery. It doesn't matter how we find the basic feasible solution. We just need to have one to start the process. We're choosing a specific problem where we can find that basic feasible solution to stop the process. Now we run the machinery on this cost function. What is the smallest possible cost we could get? 0. We may not get it. And what's the only way we get 0 as a cost? All the z's are zeros. Smallest possible cost is 0. Happens if and only if all the zi equals 0. So now we run phase 2. And what does phase 2 do? Phase 2 will take a basic feasible solution and find an optimal solution, or give us a sequence of feasible solutions with cost going to minus infinity. Is it possible for the cost to go to minus infinity? No, cost can't go to minus infinity. The cost is bounded by 0. So I'm saving this for later. Cost is greater than or equal to 0, cannot go to minus infinity. So we get a basic optimal solution. I don't even care if it's basic, we get an optimal solution. So there's two possibilities. Case 1, optimal cost is 0. So what happens if we have a solution where the optimal cost is 0? What would that mean? So, I'm sorry?
B is 0.
No, B is fixed. B is given to us. So what would it mean B is given to us? Did you say B or did you say something else?
I said B.
Okay, yes.
That means we've achieved an X that exactly hits the minimum of all our constraints and is strictly equal.
Yeah, so exactly. So if the cost is 0, all the z's have to be 0, and then we've actually solved ax equals b. Because if z is 0, that's the only way the cost can be 0, because the z's are non-negative, then we don't have to worry about this I times z. And then we just get ax equals b, and the x's are greater than 0. So this gives us ax equals b, x greater than or equal to 0, feasible to original. Question?
Could you explain what it means to extend A by over?
So I mean, if my matrix A was 2, 3, 1, 4, 1, 8, if I extend it, I'm just adding.
Okay, yeah, sure.
Okay. So do we agree that in case 1, if there's an optimal cost of 0, we found a feasible solution to the original problem? And if we have a feasible solution, can we convert it to basic feasible? Yeah. And then just convert it to basic feasible. We know how to do that. So in case 1, we're done. So what's the only remaining case? Yeah, so case 2, optimal cost is greater than 0. I claim that this implies that there can't be a feasible solution. If there were a feasible solution, what could you take for z? So let's imagine there was a feasible solution to this, to ax equals b. What could you take z to be?
0.
0. And what would the cost be? 0. So if there's a feasible solution, then there's a solution to this new problem with cost 0. We just showed that the optimal cost is greater than 0 in this case. Can't be a feasible solution. So no feasible to original, as that gives a cost of 0. And this completes the proof of how phase 2 implies phase 1. If we can do phase 2, we can always find a basic feasible solution to the original problem or prove none exist. Now, it does seem strange because phase 2 is using as an input the existence of a basic feasible solution. But what we're doing is we're not taking a basic feasible solution to the original problem. We're saying if we take this related problem where we know a basic feasible solution exists, we can then use that to analyze the original problem and prove whether or not a basic feasible solution exists for that. So we're really looking at two linear programming problems at the same time and trading off between the two of them. And we choose a new problem where the solution is staring us in the face. Take z equals v. So we've got a feasible solution, and now we just run through the machinery. Right. Any questions on this? So this is half of the proof of the simplex method. So in Wednesday's class, we'll do the other part. We'll show how to do phase 2. Given a basic feasible solution to the original problem, how do you now construct a sequence of new solutions? We're not going to prove how quickly it works. That's beyond our first course in the subject. But what we'll do is we'll show that it works and it converges. And the amazing thing is most of the time it converges extremely rapidly. So think of it as the Euclidean algorithm. Our initial analysis showed that the Euclidean algorithm for x and y could take order x steps. But then we showed it took on the order of log x steps. It was much faster than expected. What's going to happen when we do phase 2 is we're going to have to be making choices. We're going to be swapping out components of our solution. And depending on what the cost is, we're going to have good swaps. We're going to be doing good decisions. Think of it as you are trying to find a critical point for a function. The gradient tells you which direction to move. So not only does it tell you a condition, am I at a maximum or minimum, it tells you if I'm not, here's a really good direction to try going. It may not be the best direction to go. What's locally best may not be globally best, but it's not a bad thing to try. Okay, any questions on all of this? Just barely fits on the board. Okay, we're all good with this. Okay. So, one of the things I want to do is treat this somewhat like a capstone class, pulling in a lot of the math you've hopefully seen over a couple of years, show you how it's all used. And try to find representative examples of what we're doing where the prerequisites aren't as bad. So rather than going through the details of the proof of how quickly the simplex method runs, that's a great project if somebody wants to do something for this course. I want to look at similar algorithms. How many of you have looked at Newton's method? How many of you do not know what Newton's method is? How many of you are still asleep right now? Hi. You should not be able to graduate without knowing a couple of things. One of them is Newton's method. When I was a sophomore at Yale, I took a beautiful class on real analysis. And we used, it's either called the Blue Book or Baby Rooted. And any analyst knows exactly what you mean when you say that. And in chapter 3, there was a sequence of 3 problems on trying to approximate roots. And your problem 16 was using Newton's method to do square roots. Problem 17 was a different method, which wasn't nearly as good. And problem 18 was a generalization that does general p roots. And what I want to do is I want to show you Newton's method because this is a great problem in terms of how quickly you can do things. Things move a lot faster than expected. It's a great way to see how the more math you assume, the more you assume about your system, the more you can prove. And it will give us a good way to talk about how do you find solutions to problems. Later in the semester, we're going to talk about fixed points. And so this is a great way to find fixed points. So this is putting some material in the bank for later. So we're going to do a little battle. Does Conquer have an E at the end? No. Okay. So do my computer scientists know about divide and conquer?
Yeah.
All right, this is one of the most famous algorithms. It's a great algorithm. So divide and conquer versus Newton's method. So the goal is to find solutions to problems. We want to find roots. So we want to solve, say, f of x equals a. So for both of them, we want to find f of x equals a once solve this. If you don't want to do f of x equals a, if you want to do f of x equals 0, that's fine. You just change your function by subtracting a from it. So finding where a function equals a specific value, finding root, these are all the same. This is one of the most fundamental things in mathematics. So now we see the importance of finding roots. Later on in the semester, we'll be looking for fixed points, f of x equals x. If you can solve fixed points, you can go back and forth between all these things. Here, I'm going to assume my function f is continuous, and here I'm going to assume f is continuous and differentiable. If you had to make an assumption, which assumption would you rather make? Continuous or continuous and differentiable?
Just continue.
Just continuous. Why?
It's more often true.
It's more often true, right? This is the more inclusive choice. Anybody want to give me the other camp? Yes?
You can do more with it.
You can do more. Now all of a sudden the tools of calculus are available. So it's more restrictive, not as many things satisfy this constraint, but those that do, you can now argue more. This is the trade-off we often have. So the way divide and conquer works is it uses the immediate value theorem. So without loss of generality, our interval is 0, 1. If the function is positive at 0 and negative at 1, what must be true if it's continuous? Has a root between them. So we now cut the interval in half, and let's say it's positive there. What do we know? There's a root between a half and 1. What about between 0 and a half? Is there a root between there? I like the answer anyways. Maybe. Right? We don't know. The function could go down, up, and then back down because it was negative over here. But we know there must be a root between 1/2 and 1. So we divide again, 3/4. Let's say it's negative there. Now we know there's a root between 1/2 and 3/4. So every 10 iterations, error decreases by approximately what? So if we were to do this 10 times, what would happen to the error? Yeah, by about 1/2 to the 10, which is about 1/1000, so about 0.001. Okay, so basically every time you do this, the interval of uncertainty halves. So you do this 10 times, you save a factor of 2 to the 10. 2 to the 10 is about 1,000, 1024, but 1,000 is close enough. So you basically get 3 digits every 10 iterations. So if I want to find the square root of 3, I can look at f of x. So for square root of 3, I could take, f of x equals x squared, and set that equal to 3, and apply divide and conquer. And every 10 steps will give me 3 digits. Okay? What I want to do is I want to show you Newton's method. This is one of the reasons why calculus is so great. The whole idea, or one of the biggest ideas of differential calculus, is you replace any nice function locally with a straight line. Because if you had to choose what you want your function to look like, you would choose a straight line. Okay? So let's say so here's my function, f of x is x squared minus 3. I'll do it this way. So I'm trying to find the root of this. And the root of this is going to be plus or minus square root of 3. Okay? The way Newton's method works is you start off with a guess. I don't want a particularly good guess for the square root of 3. Somebody give me an okay guess for square root of 3. 2. Good. It's a better guess than 1. So we'll start off with 2 as my initial guess. So what I do is here's 2. I go up to this point, and this point will become 2f of 2, and I calculate the slope, and then, based on how I've drawn it, I'll put 2 a little bit over here. And I can calculate the slope of the tangent line. what's the slope of the tangent line? 4. And so it's going to just be the slope is f prime of 2. And what I can then do is I can flow on the tangent line and find where the tangent line hits the x-axis. And if this is my first guess, this will become my second guess. This will be my x1. And then lather, rinse, repeat. We do the shampoo method. We come up here. We would now have the point x1, f of x1. And you can see, proof by your chalk picture, that already at 2 iterations, it's a really good approximation. So in general, if we have the point xn, f of xn, and slope f prime of xn, the next point, we get the equation of the tangent line as following. So y minus f of xn equals f prime of xn x minus xn. Everybody remember equations of lines? So how do we find xn plus 1? That's where y equals 0. So y equals 0 gives us xn plus 1, just do the algebra, it's going to be f of xn divided by f prime of xn with a negative sign, and then move xn over. Right? And so when the dust settles, after some algebra, if memory serves, we'll get something like xn plus 1 is 1/2 xn plus 3 over xn, after you do the algebra. And what's nice about this is if you take, what value would you love to take for xn? I'm sorry? What value would you love to take for xn? I'm sorry?
The limit?
Yeah, what would that limit be?
Infinity.
I'm sorry?
Infinity.
Not infinity. Root 3. But we're trying to find the square root of 3. So if you actually plug in xn equals root 3, you get root 3 plus 3 over root 3. That's 2 root 3. Divided by 2 is just root 3. So it sends the solution back to itself. And it's going to send anything close to the solution even closer. So I wrote ahead of time the square root of 3 on the board. What you can do is you can apply this and you can start getting different approximations. What's nice is you're always going to get rational approximations if you start with a rational point. And so the first one, you get x1 equals 7/4, which is 1.75. That's not bad. Really simple, just doing one tangent line. All right? x2, and again, I have no desire to memorize these, is 97 over 56. So x2 is 1.73214. What do you think? Remember, I mean, we're off by essentially 9 out of, that's pretty far down. Let's do it one more time. x3 equals 18817 over 10864. And these are not that bad to find. I mean, this is just manipulating rationals. If you do that, x3 is going to be 1.7320508 100. So instead of 0.75, we're off by that, not that much more. x4 is 708.
Wait, those are equal at x3, aren't they?
I'm sorry?
Those are like effectively equal to
The square root of 3?
no, and then like to all of those decimal points. No, both x3 terms. The fraction on the left,
This one over here?
yeah,
Yes.
is equal to one on the right plus like 5 digits past the decimal.
Right. I've just stopped writing digits here because I'm no longer equal to square root of 3.
Alright.
I'm just doing the comparison to just show you how good things are.
Yeah.
So if I do x4, I get 7, 0, 8, blah, 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 blah. We don't really care what these numbers are over 4, 0, 8, blah, 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 blah. X4 is 1.7, 3, 2, 0, 5, 0, 8, 0, 7, 5, 6, 8, 8, 8. If I were to do x5, the error is approximately 8.61 times 10 to the negative 37. Yes?
How did you get the 3 in the last equation there? Because that's the limit we're trying to approach.
Well, I know what f of xn. F of xn is xn squared minus 3. F prime of xn is 2xn. You just take these and you just substitute it. So, if this does not excite you mathematically, I apologize. We need to talk. Okay? 5 iterations, and we have essentially 37 decimal digits of accuracy. Divide and conquer, we do 10 iterations to get 3. Okay, this is the biggest difference I can think of between two methods that I can easily explain on the order of 5 to 10 minutes. Divide and conquer is a wonderful method. It's very nice, it's easy to use. It's applicable in many cases where this is not, but it's slow. Here, essentially every time you apply Newton's method again, you double the number of digits of accuracy. You quickly reach the point where you're overflowing what your calculator can do, as you apply Newton's method. There's a lot of great connections between this and fractal geometry. But you can ask us, well, what if I have multiple roots? Which root does it converge to? And you can draw pictures in the plane. Let's say I have a cubic, so I have 3 roots. Which root will it go to? When does it go to the root that's closest? And you can color every point in the plane a color based on what it goes to. And so I'll put some links where you can look at all these wonderful fractal pictures. But to me, this is a great way to just emphasize the difference between having an algorithm and having an efficient algorithm. Divide and conquer is an algorithm. It will find the solution, but slowly. Newton's method will find it quickly, but it needs some additional assumptions. And these assumptions are often met. So think of all these constraints we're putting on when we're doing linear programming problems as just reasonable constraints. Okay? And then we will use this later when we get to fixed points, but this is also a great example of how calculus. And if you want to find p roots, you can just put something over here and figure out how that changes to find p roots. Okay. Any questions on Newton's method? Yes?
Is there any function that's like a degenerate case for Newton's method where divide and conquer would be better? That is differentiable?
Probably, because there are some methods, there are some problems where if you don't have the right concavity of your function and you have a bad initial guess, you could get caught hopping between various places. So it's possible to jerry-rig something where Newton's method will have problems. If your function is nice and if you're sufficiently close. So what could you do to make sure you don't have this horrible situation of hopping around?
Try a few initial guesses.
I'm sorry?
Could you try a few initial guesses?
You could try a few initial guesses. How could you get those initial guesses? What could you use? You use divide and conquer, right? Think of it as like a rocket booster. You use divide and conquer for the first stage, and then after you get to somewhere close, kick it away. And now that you're close to the root, now you use Newton's method, which is better. So that's a really good way. A lot of algorithms work this way. You have something that works well in one regime, and you use it for a little bit, and then you switch to the more refined one. Or sometimes you have something where you don't know, it's going to be fast in almost all inputs, and every now and then it's going to be damn slow. So you run it for a while, and if the computer isn't halting, then you stop and you use the slow algorithm, and you just know you won't have to use the slow algorithm too many times. Okay, so I wanted to end the day with talking about the chess problem. So we looked at, in class, if you have a 5x5 board, you want to put down 5 queens so that 3 pawns are safe. I never proved in class that you can't put down more than 5 pawns safely no matter how the queens are placed, but as several people have commented to me, I wouldn't be giving the problem like this if I could have done better than 3. It's possible maybe I'm keeping something in reserve. I have stories like that, but I will not say them when the camera is rolling. It's how you negotiate with administration. You sometimes do keep a couple of chips that you don't want publicly available, but for this problem, the best you can do is 3. So we have the following. So n by n board, place n queens to maximize the number of pawns that are safe. And we'll call that number P of n for pawn of n. And so we have a couple of values. Somebody from the class got me 0, 0, 0, 1, 3, 5, 8, 7, 7, 7, 11, 18, 22. Is that basically what we repeated out?
30.
Oh, 30? Okay, excellent. So what you do is shove into the OEIS, and it will recognize the sequence, and it will give you some information about this. The more terms you have, the more you narrow down what's in the OEIS. There are a lot of times when I've used the OEIS to prove results by getting an idea of what I should try to prove by induction. Sometimes it will give you formulas. For this one, I think this is an open problem as to what is P of n for general n. Now, when you look at the first couple of values, and you can look at what fraction of the board is safe, very little of the board is safe initially. But is the percentage increasing or decreasing? So here is 1, 2, 3, it's 4. So this is 1/16 versus 3/25. I'd much rather have 3/25 than 1/16. So it does look like the percentage is increasing. How high do you think it increases to? In the limit, do you expect almost every square to be safe or almost every square to be killed? So if you count primes, we're both counting primes. If you count primes up to x, the number of primes up to x is about x over log x. So the number of primes is growing, but almost every number is not a prime. So here, do you think in the limit 100% of squares are safe? So I've got one person saying yes, 2 people, 3, okay. So we want to try to get upper and lower bounds for P of n. So I'm going to say a little bit about that, and at this time I'll let people who bridge and code say a few things about how they did the coding. So we want upper and lower bounds. I think it's easier to find a lower bound. The reason is, if you can find one configuration, analyze that configuration, and figure out how many pawns it allows you to place, that gives you a lower bound. An upper bound, you have to do something that works for everything. So years ago, I was working with a number theorist and a couple of computer scientists to prove that a certain type of circuit with a given efficiency could not be built. And we were able to show it couldn't be done with n or fewer vertices. And we were able to prove that for larger values of n, almost any choice would not work. Well, in some sense, that's almost useless. I don't really care if most configurations don't work. If there's one configuration that works, I'll use that one. So it gives you an idea of maybe how likely it is that you'll find something. So what I want to do here is I want to find a good lower bound. So to find a good lower bound, I want to choose a configuration. One of the things we want to do is we want to minimize the number of squares that are killed. So we want a lot of queens killing common squares. Anybody think of a good way to pack queens to try to minimize the different squares that are killed? Corner. So what we could do is we could take a large board and put a bunch of queens in the corner. So when I first did the problem, I assumed my board was n equals m squared by m squared. And I had an m by m subboard, subsquare down here. If you don't have a perfect square, what you do is you take the largest integer less than the square root. Okay? I'm not going to really worry about putting in the floor function right now. So, and I'm not going to worry about my constants and whatnot. I just want to give you the general idea of what you would do. So if we had an n by n board, if I look at the root n by root n subboard down here, that'll give me my n queens. And let's see how many squares this kills. If I look at the columns, the main term of that is going to be n times root n. The stuff down here, that's a low order term, right? That's going to be of size n. This is of size n to the 3/2. If I look over here, that gives me another n root n. And then I have to do these diagonals. What's that going to be? So worst case scenario, I have 2n minus 1 diagonals. Each diagonal, I'm sorry, 2 root n minus 1 diagonals. And each diagonal is at most n. So something like that.
Is it appropriate to say each diagonal is the most n?
Right.
Or
Each diagonal will have at most n elements. And so this will give me a bound for how many things can be killed. And so this is going to be on the order of 4 n to the 3/2. So the number of safe squares is at least n squared minus 4n to the 3/2 plus lower. Okay. Question? Okay, so this gives me a lower bound. And again, I can do a little bit better than the 4 because this is not going to have maybe as many elements as this, but since this is of size square root of n, probably to first order all these diagonals have n terms, right? And it's going to just be a lower order. What I really care about is that the term here is of size n to the 3/2. I don't really care about the n term. I do care about what constant this is. I do believe 4 is the right constant. I think the fluctuations is negligible here. They all have approximately n elements in each diagonal. So here's a configuration where I can place n squared minus 4n to the 3/2 terms. All right. Now let's try to do the upper bound. Upper bound is harder, and that's what I really want to talk about. Can somebody give me an upper bound? Better than n squared. Yes.
n squared minus n.
Great. Wow, wonderful. Fine.
It's bad.
Yep, and that was the best I had for a while. Okay? So I thought really hard to see, can I do better than this? Because the problem is, the n here and the n to the 3/2 are different orders of magnitude. And I want to know, what is the correct scale for the number of safe squares? Is it of size n, n to the 3/2, something in between? What's the right answer? And so I came up with the following. So consider a configuration. Assume f of n rows have a queen. I'll just let f of n denote the number of rows with a queen. So this kills f of n times n squares. It kills more than this, but it kills at least f of n times n squares. Because each row that has a queen, all n things in that row are killed. So do we agree that at least this many squares are killed, if we just look at it rows? Now let's look at it in columns. Each column has at most how many queens? What's the maximum number of queens that could be in a column? I'm sorry?
N.
Initially n, but because of this assumption, it's better than n.
And minus f.
Nope. It has at most f of n. We have at most f of n rows that have a queen in it. If one column had more than f of n queens, then we would have more than f of n rows with queens. So each column has at most f of n queens.
Can you say that one more time?
We know that there's at most f of n rows with queens. Right?
Right.
So there's got to be at least, so we can't have any row, so we can't have any column with more than f of n queens.
You're talking about each column, not the number of columns.
We've got to look. I will continue this.
Okay, yeah, yes.
I will continue this on Wednesday. I don't want to rush to this because this is a good idea.